So I, Shankar Tripathi, welcome you all on behalf of GATE Academy in the fluid mechanics last score booster session. So my dear students, this is the last score booster session of fluid mechanics. So we already have completed two score booster sessions. We already have completed two score booster sessions of fluid mechanics, and this is our third score booster session. This is our third and the final score booster session. So live student, good afternoon. I welcome you all again on the GATE Academy English channel. Good afternoon, Vijay. So this is our fluid mechanics score booster session, and my name is, as I said, Shankar Tripathi. My name is Shankar Tripathi, and I am a PhD scholar at IIT Roorkee. So PhD scholar, we people are usually called upon as research scholars as well. So currently, I am a research scholar at IIT Roorkee. So before enrolling into this PhD program, I have completed my MTech from IIT Roorkee itself. Now, talking about my GATE history, I am fine. Priyavata, I am very fine. So GATE 2014, I had this much marks, 65.66 with all India rank of 916, and in GATE 2015, I had 76.02 marks with all India rank 643. With all India rank 643. All right. Hello, Tapan. So this is about my GATE history. So I can tell you something from my own experience. I also have discussed this in the previous school booster sessions that 5-6 marks 5-6 marks in GATE examination 5-6 marks in GATE examination are very crucial in order to achieve a better rank, a good rank, and as all we know, if we are getting a better rank, the opportunities that we are going to get are going to be very better. Okay. So what is the purpose of this score booster session, as we have discussed in the previous session also, that we want to have a revision. We want to have a revision of this whole fluid mechanics subject in these score booster session, along with some good question, along with the discussions of the formula, along with the discussions of the formula, along with that what is things that to be taken care while using some formula. So as I said, I previously also have showed you the margin of, in the previous sessions also I have shown you the margin of this fluid mechanics in our GATE examination. So this you can see a brief analysis of what percentage of marks that are getting asked of various subjects in different GATE years. So from 2012 to 2020, you can see the margin of fluid mechanics in this slide. Shantanu, we cannot certainly comment upon any of it. Okay, this is impossible to comment whether the question will be simple, which will not be simple. See, this is not in our hand. Yes or no? Is this in our hand? That the new topic that got into this GATE examination, the question will be asked as simple on. This is not our hand. What is in our hand? That we can make our preparation as much as we can do. Yes or no? Yes or no? We should be prepared. We should be prepared as much as we could. This is the only thing we can do. Hi Vijay. Good afternoon. So we can see the margin of this fluid mechanics. So all over, we can say that this is somewhat around 8% in your GATE examination. So this fluid mechanics is having a margin of, I am fine, Vijay, I am fine. So this fluid mechanics having a margin of this 8 marks in your GATE paper, and this 8 marks, believe me, that if you can obtain 5, 6, 7 marks out of it, then it is a great thing. It is a great thing. So in this score booster session, what we are trying to do, we are trying to cover as much as of fluid mechanics that is possible. So in the previous sessions we have completed up to this point. We have quickly reviewed the kinematics, till the kinematics, fluid statics and kinematics. We have revised the formulas of them. Yes or no? We have revised the formulas of them. We have done some questions of them. We have seen that while using which formula, what cares needed to be taken. So in this today's session, we are going to continue with the same approach. And here I open again the formula sheet I have prepared for you guys. Here I open the formula sheet for you guys. So now in today's session, we are going to begin with the fluid dynamics part. Now, see, if you memorize, if you remember, what do we guys see in the fluid dynamics? So we mostly see this. That is what I have already highlighted, this Bernoulli equation. We mostly see this Bernoulli equation. Yes or no? And this Bernoulli equation is derived from which equation? It is derived from this Euler equation. It is derived from this Euler equation, which is a force equation, beta. Which is a force equation. So from using this equation, with the use of this equation, we can derive the Bernoulli equation. So if you derive, now remember this, if you derive considering the flow to be incompressible, this will be the most important equation. Now, why I am saying this is the most important equation, beta? Why I am saying this is the most important equation, beta? Because if you see the GATE questions, or if you see the further chapters like pipe flow, compressible flow, vortex motion, so they are nothing but the applications of it. So sir, you will say, sir, this equation that you are showing to us, we have seen this equation a lot of times, because even in the semester, if you can relate to it, even in the semester, this helped you a lot in passing the semester. Yes or no? Yes or no? So in Bernoulli equation, beta, what is needed to be done? You all know, sir, that, sir, we should apply the Bernoulli equation. We shall apply the Bernoulli equation between 2 points like this. So if there is a problem like this, let us call this is to be Z1. This is to be Z1, that is 5 meter. Let us call this is Z2, that is 10 meter. So if some pressure at P1 is given to you for say 100 kilopascal, the velocity at V1 is given to you, let's say 5 meter per second. The diameter at this section is given to be, let's say, 50 mm. On this section 2, the velocity, let's say, is given to be, is not given. Velocity is not given. Diameter is given to be 100 mm. Okay. You need to find the pressure. Then you will say, sir, this looks like very simple question. This is something looking like very simple question. If we see a question like this, we will certainly apply the Bernoulli equation like this. Now, in this equation, sir, we need to find our P2. So in order to find the P2, we have the Z1, we have the Z2, sir, we have this V1, we have this P1. So if we can find our V2 from this equation, we can easily find our P2. So, sir, how to find this V2? So, sir, we will apply this continuity equation. We will apply this continuity equation, and we'll be able to find our velocity as section 2. And this question will be done. This question will be done. Now, sir, please tell me frankly, please be frank with me. And you have to respond, and live student have to respond. Now, please tell me this kind of a question, if you see, very certainly you will be able to solve. Do you relate with this or not? That in semesters also, this Bernoulli equation helps us a lot in getting our degree, in passing the fluid mechanics semester examination. Yes or no? Yes or no? Yes or no? Okay. So in all the Bernoulli equation, remember this. Somehow you have to apply the continuity equation as well. Somewhat you have to apply the continuity equation as well. Now, now, in GATE examination, beta, what happens? In GATE examination, what happens? This is my analysis of this Bernoulli equation in the GATE examination. Now, if they give this kind of a question, sometimes they give this kind of a question as well. This kind of a questions as well. So if they give this kind of a question, we will be very easily be able to solve it. Now, what they will do now? What they will do now? They will play with the fear of the students. This is my analysis of how they are putting the questions of this Bernoulli equation in the GATE examination. So they are trying to play with the fear of the students. That simple Bernoulli equation is very simple. All of us do agree with it. So they will frame the question in a way that you will have some fear in your mind. Some fear will come in your mind. This kind of a question we have never seen. We have never seen like the question I am going to show. Just a GATE question. A GATE question. Okay, so this is a GATE question you can see on your screen. This GATE question is being asked in 2 marks in 2003. So in this question, this is a simple Bernoulli equation question. But in this question, how they have framed this question? How they have framed this question? In this question, they have put some spring. They have given some stiffness of the spring. They have given some compression of the spring. Okay. So instead of making it applying the Bernoulli equation, so making it a question of that you find a variable in a equation, they have framed it in a different way. They have somewhat framed it in a different way like this. In a different way like this. Now, in order to solve this question, what can be done? What can be done? So let's say this section is 1, 1, this section is 2, 2. So if you read this question, just go through this question once. So if you read this question, they are asking, what is this X? In this question, beta, they are asking this X, okay, this compression, and they have given the options like this. They have given, beta, the options like this. Getting my point? Getting my point? So when you see this kind of a question, you will have some fear in your mind. So this is my first score booster tip in this dynamics part, that please do not have some fear. Okay, just identify this, that we only have to apply the Bernoulli equation here in this question. So if we apply the Bernoulli equation, so you have to find X. You have to find X. So stiffness is given. So we all know, sir, stiffness is force upon displacement. Yes or no? All of us do know it or not? All of us do know it or not? Yes, sir. We all know that stiffness is force upon displacement. So, sir, what will be the displacement? Sir, it will be force upon stiffness. Sir, it will be force upon stiffness. Yes or no? Yes or no? Now seeing this equation, can we say if we can somewhat find the F, if we can from somewhere find this F, we will be able to get the X. How I am trying to relate with the things, are you getting my point or not? Yes or no? Yes or no? Now, how we will get the force? How we'll get the force? So by seeing this question, you have this Venturi meter. So Venturi meter questions are solved by using the Bernoulli equation. So once you see the Venturi meter, the things that will first come to your mind, that somewhat Bernoulli equation is to be applied. Now, when the Bernoulli equation is to be applied, this force we have to find. Now, from Bernoulli equation, we can find the pressure. Yes or no? We can find the pressure of one using Bernoulli equation. Now, once we have this pressure, we can multiply the area. into the pressure, we will be getting the force. We will be getting the force. Yes or no? Once we are getting the force, we will be getting displacement by putting all the values in this equation. By putting all the values in this equation. So, beta, what I am trying to tell you, please listen to me very, very carefully. What I am trying to tell you that in these kind of questions, please do not be in any fear. Okay, just try to recognize. I always said this was to all of you that, sir, in examination, first of all, you have to identify the subject. So if you see this question, I am very much certain that all of you will be able to understand that this is a fluid mechanics question. Now, once you understand this is a fluid mechanics question, then try to recognize the topic. This is the way how questions are getting solved in the examination, in the GATE examination. So once you understand that this is a dynamics question, then remember the point I'm giving you, that if it is a question of dynamics, mostly it is going to be done by the Bernoulli equation. Now, in Bernoulli equation, we say once this comes into your mind, that Bernoulli equation, then things will go flow. That's a Bernoulli equation we need to apply between two sections. So this is section 1, this is section 2. So we are going to apply Bernoulli equation between 2 points. We will put the necessary data, we will get the pressure, then we multiply this pressure with the area, we will be getting the force, and we will be getting the displacement. Is that done or not? Clear or not? In a similar way, I am just trying to show you that how they are making the question. Now see this question also. This is also, in this also you have to apply Bernoulli equation between 2 points. What is the difference they have given in this question? What is extra they have given in this question? So they have given this 100 kg extra in this question. Okay, we mostly see questions like this. Previous session also we have seen a question like this, that if velocity is here, if like this is h, we can find the velocity of flow by doing rho g h. Yes or no? We can apply Bernoulli equation between section 1 and section 2. Now in this question they have just placed one extra mass over here. So while applying the Bernoulli equation, you have to consider the pressure given by this mass. But for instance, believe it or not, when you see this kind of a question very first time in the examination, you will feel that, sir, I have never done a question like this while I was practicing. This is where GATE plays with the brain of the student. Okay, this is a common tendency. That if you see a question that I have showed you previously, you will be confident. I have done this kind of a question before, so I will be able to do it. But if you see this kind of a question, you will see something new is in this question. It looked like something new. So something new is looking like into it. So we will be not that confident that we will be able to do it. Then please remember this score boosting tip that I am giving you, that please recognize the topic from which the question is being asked. Okay. Similarly, if you see in this question, in this question also, they are asking what is the force. In this question also, beta, they are asking what is the force on this plunger. So all you have to do is apply Bernoulli equation between 1 and 2, and get the pressure at 1, multiply it with area, you will be getting your force. Now, in this, instead of making it simple, they have given you a syringe and something. So why they have giving it like syringe and something, so as that you will feel in a way that syringe, we have never seen a question of syringe before. From where the syringe, what concept is to be applied, do not worry about it. Just try to recognize which subject the question is. So am I clear about it or not? So from the questions I have shown you, I just wanted to prove this point. That in case of Bernoulli equation, which we all which we all consider to be very simple. So please keep it simple. And when it is to be applied in the question, just remember that in the dynamics, we have only this equation. In dynamics, we have only this equation. In dynamics, we have only this equation. Okay, in dynamics, we have only this equation to be applied, and we can do it. If force is asked, we can find the pressure, we can multiply with area. Okay, so this, can I put a tick over here? Is this clear or not? Is this clear or not? Can I put a tick here, beta? Sujit? Now coming to the next thing, in this dynamics portion, we see the analysis of Venturi meter, pitot tube, yes or no? Yes or no? Now, this is something very important formula. This is one more very important formula. This is one more very important formula. This is one more of a very important formula that is generally getting used, that is generally getting used in the dynamics part. Now, where to use this formula, beta? Where to use this formula? When you have manometer given in the question. When you have some manometer given in the question. Okay. So if a YouTube manometer is given in the question, beta, if a YouTube manometer is given in the question, then you have to use this first formula. And if a inverted YouTube manometer is given to you, you have to use this reverse formula. You have to use this reverse formula. Getting my point or not, beta? Getting my point or not, beta? Getting my point or not, beta? Please tell me. Getting my point or not, beta? Please tell me. Please tell me. Please tell me. Getting my point or not? Yes or no? Now let's do one question based on it. Let's do one question based on it. So can you see this first question? Can you see the first question here? Let's try to solve it. Let us try to solve it. Let us take 2 minutes to solve it. So I hope now you can see it. I hope now you can see it nicely. Yes or no? Yes or no? Yes or no? Please try to do it. Please try to do it. You are here with your calculators and all now. Please try to do it and give me the answer. So if we read the question, so air flows through a pipe at a rate of 170 liter per second. So what is this 170 liter per second? This is the discharge. Yes or no? So if I convert it into meter, it will be 10 to the power minus 3 meter cube per second. Do we know it how to convert liter per second into meter cube per second? So you have to multiply 10 to the power minus 3 into it. Yes or no? Yes or no? Now the pipe consists of two sections of diameter 18 centimeter. Two sections of diameter 18 centimeter. It consists of two sections of diameter 18 centimeter. So let us say this is 18 centimeter. And 10 centimeter with a smooth reducing section that connects them. So it is our 10 centimeter. This is 10 centimeter. The pressure difference between the two pipe sections is measured by a YouTube water manometer. So if I apply a YouTube manometer between them, so pressure difference between these sections 1 and 2, pressure difference between these sections 1 and 2 is getting measured by a YouTube water manometer. Neglecting frictional effect, the differential height of water between the two pipe section is. So in this, the manometric fluid is water. In this, the manometric fluid beta is water. So what is to be found in this question? What is to be found in this question? This X is to be found. Getting my point beta or not? Please say yes or no. Yes or no? So in this, what is to be found? This X is to be found. And this is air. And this is air. This is water. Now, how we can do it? Now, sir, first question that you may ask me, that's why you have taken the level of manometric fluid down here. Why you have taken the level down here? Why it is up? Because pressure at 1 will be more. Obviously, sir, pressure at 1 will be greater than pressure at 2. Why this so, sir? Why this so? By the law of conservation of energy, we know it or not. Since the cross-sectional area for incompressible flows, the cross-sectional area here is more and cross-sectional area here is less. So in that case, the pressure at this section is certainly more the pressure in this section. So if I apply Bernoulli equation, it will be like this. If I apply Bernoulli equation, it will be like this. Yes or no? Between 1 and 2. If I apply simply Bernoulli equation, it will be like this between 1 and 2. So in this, since the level are same, since the datum is same, so I can cancel Z1 and Z2. And I can write like this: P1 by rho G minus P2 by rho G. P1 by rho G minus P2 by rho G is equal to V2 square by 2G minus V1 square by 2G. Say yes or no, beta? Say yes or no? Yes or no? Now, in this discharge is given, so we know, sir, A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2 is equal to discharge. So your discharge is 170 into 10 to the power minus 3 meter cube per second, and you are given with the diameter 18 and 10. So we have this A1 pi by 4 D1 square V1 is equal to 170 into 10 to the power minus 3. So from here we can get our V1. Yes or no? From here we have this D1. So from here we can get our V1. Yes or no, beta? So it is coming out to be, if you calculate it, it is coming out to be 6.68 meter per second. 6.68 meter per second. Similarly, if I want to find this V2, so it is pi by 4 d2 square into V2, pi by 4 d2 square into V2. So it is 170 into 10 to the power minus 3. So your V2 will come out to be, if you calculate it, it is coming out to be 2.645 meter per second. So please cross check the calculations also. Yes or no? Beta? So we have now this. We can find this now. We can find this now. Yes or no? We can find this now. Yes or no? Yes or no? Yes or no? Now, what is this P1 minus P2 by rho g? So, can I say this P1 minus P2 by rho g, P1 by rho g minus P2 by rho g, it is the pressure head difference. It is the pressure head difference. Please be careful here. Pressure head difference between 1 and 2, between 1 and 2 in terms of, in terms of, in terms of fluid flowing through pipe. Yes or no? Yes or no? Yes or no? Why, sir? In terms of, why you are writing, sir? In terms of fluid flowing through the pipe, because we are using the density of that fluid only na. We are using here the density of that fluid only na. So this is the pressure head difference. This is the bit of pressure head difference. This is the pressure head difference between 1 and 2 in terms of fluid flowing through the pipe. In terms of fluid flowing through the pipe. Now you have to get this x. So if I applied the manometric equation, so let's say this is 1, this is 2. So I told you in the previous score booster session that how to solve a manometer problem, how to apply the manometric equation, how to get the pressure in a manometer problem. So in the same way if I do, so I shall write H1W. What were the rules we have seen? Remember, in the formula sheet I have shown you the rules. What were the rules? We have explained it in the previous score booster sessions, where this points to remember while solving a manometer problem, that is change everything to water, do addition if moving downward, do subtraction if moving upward. Remember these or not? Remember these or not? Please tell me. Please tell me, remember this or not? Yes, sir. Yes, sir. Is it or isn't it, beta? Is it or isn't it? Please respond. Now, if I apply the manometric equation, so I shall convert it into water. So this is H1W. Moving downwards. So let's say from this to this, we have moved by y distance. So this H1W plus S1Y. Let's say the specific gravity of this fluid is S1 or S maybe, or let's say S. Okay, so SY plus SX. So we have reached till this point. Now from this point to this point, we have nothing to do. From this point to this point, we have nothing to do. So we can move upwards. So we can do the minus. So we are moving in water. Let's call it manometric fluid. So SM. So this is SM into X. This is minus SM into X. We have reached till this point. Now from above we are moving by y, so this will be minus sy is equal to h2w. So this sy will be cancelled out, and h1w minus h2w is xsm minus x. xsm minus x. Yes or no, beta? Yes or no, beta? Now, sir, is this, or if I call it H, so is this H and this is same? So sir, no, because this is pressure head difference. This is pressure head difference in terms of water. Yes or no? We have written it now, H1W minus H2W. So this is pressure head difference, beta, in terms of water. This is pressure head difference, beta, in terms of water. Pressure head difference in terms of water. In terms of water. Yes or no, beta? Yes or no, beta? Okay, this is pressure head difference in terms of water. Understood or not? Understood or not? Yes or no? Yes or no? Okay. So if this is pressure head difference in terms of water, if this is pressure head difference, beta, in terms of water, so what we need to do? what we need to do, we need to convert it. We need to convert it. We need to convert it in our in our in our fluid flowing through the pipe. So in order to convert it in terms of fluid flowing through the pipe, we need to multiply it with the specific gravity as we have seen. So if the fluid flowing through this pipe is having a specific gravity of S, we can convert it in terms of S like this. So this will be X Sm minus S, X Sm minus S, yes or no? Yes or no? Now from here, can I write X is equal to Sm by S minus 1? Now this is the formula I have mentioned in the formula sheet as well. This is the formula I have mentioned in the formula sheet as well. You can see here. You can see here. You can see here. So this I am going to highlight with this blue color. Okay. So you can see it here, beta. Yes or no? Yes or no, beta? Please tell me yes or no. Yes or no? This is the same formula. So if you even forget it, and your basic concepts are strong, if you even forget it, your basic concepts are strong, you can derive it quickly, or you can just do what we have seen in the statics about solving the manometric equation. Yes or no? Yes or no? Yes or no? Now, if I put this value here, if I put this value in this equation, in which equation? In this, let's call it equation 1. So if I put this value in this equation, so in place of P1 by rho g minus P2 by rho g, I am placing X Sm by S minus 1 is equal to V2 square by 2g minus V1 square by 2g. Yes or no? Now in this equation, we have this Sm, we have this S, we have this V2, we have this V1. So can we find our X or not? Can we find our X or not? So your X will come out to be 2.454 centimeter. You can cross check it. See, tell me, is this question understood or not? Is this question understood or not? Now, if this manometer, in this, it is simple YouTube manometer, but if it is inverted YouTube manometer, you could have used this formula. Instead of this, you can derive it also. Instead of this, you can use this formula in which I am placing the tick now. Getting my point or not? Getting my point or not? Now, if a YouTube manometer or a differential, if a YouTube differential manometer or an inverted YouTube differential manometer is placed in a Bernoulli equation problem, will you be able to do it or not? Please tell me yes or no, beta. Please tell me yes or no. Please tell me yes or no, beta. Say yes or no, beta. Very important. Very important. So can we say this Bernoulli equation is clear to everyone? Yes or no? Yes or no? The final answer is beta 2.54 centimeter. The final answer is 2.54 centimeter, Dilip. Understood? Now, our next chapter is pipe flow. So in pipe flow, beta, in previous Bernoulli equation, we have considered it for ideal fluid. Now, the only difference in this topic from the previous in this, no, beta Shantanu, X is the difference of, see, X is the difference of, see what is written? See, in this, the differential height of water between the two pipe section. Differential height of water means what? In this, air is flowing now. So it is the difference between the level of manometric fluid in the YouTube manometer. Getting my point or not, beta? Shantanu. Understood or not, beta? Understood or not? Please tell me, beta. Any doubt? Any doubt? This X and this H are different. Okay. This X and this H are different. This is not X. Remember this. Very important point. This is not X. Not X. Yes or no? Yes or no, beta? This is H, as I have mentioned in the formula sheet also. See, this is H. Understood, beta? Understood or not? To everyone? Beta, if water was flowing, now if in this case, if water is flowing, now you are asking, sir, if water is flowing, so your S will become 1, okay? Because the specific gravity of water is 1. If mercury is in the manometric fluid, so your SM will become 13.6 for Hg. So what will be your H? It will be X SM by S minus 1. So what you would have done in the same question? In place of SM, you would have placed 13.6. In place of S, you would have placed 1. Understood? In this question, in place of SM, you are putting 1 because it is water. In this case, it is air. So air density is given in the question. It is 1.2. It is 1.2. So you must divide it by 1000. Understood or not, beta? Say yes or no. How to use this formula? Is this clear to everyone or not? Please tell me. How to use this formula? Shantanu. Okay. Now coming to this pipe flow section. So in this pipe flow section, the only difference from the Bernoulli equation that we see previously is that we are talking about real fluid. So when we talk about real fluid, what happens? What happens? If we talk about the real fluid have some viscosity. So if they are having some viscosity, so certainly there will be some losses. So in case of pipe flow, the only difference is the same Bernoulli equation you are putting, the same Bernoulli equation you are applying, but with the losses. But here you also are considering the losses. Is that clear or not? Is that clear or not, beta? Please tell me. Is that clear or not? Please tell me. Please tell me, beta. So in case of real fluid, in case of this topic pipe flow, the only addition here is the losses. The only addition here is the losses. Okay. So let's see, let's quickly revise the losses but what we have learned in the fluid mechanics. As I said, beta, this is a revision session. In this, we are trying to revise so that we can boost our score. And as I said, today I will share this formula sheet with you guys. Okay, I will share this to you guys. Okay, so this is the first formula. This is the first formula that we see here, that is HF is equal to FLV square by 2GD. FLV square by 2GD. This is head loss due to friction. It is also known as Darcy equation. Darcy-Weisbach equation. Madhu Smita, you are asking, sir, but the laws in which section we have to put often confuse about it. Now, laws in which section, you please understand this. We have a pipe like this. We have a pipe like this. Now, you tell me, now this is section 1, this is section 2. Okay. This is section 1, beta. This is section 2. Now, between section 1 and section 2, flow can take place in this direction. Yes or no? Or flow may take place in opposite direction like this. Yes or no, beta? Yes or no? Yes or no? Yes or no? Please tell me. Now, always remember that the losses happen in the direction of flow. In that direction of flow, or there is a very frequent saying that you might have heard, that flow takes place in decreasing energy, in the direction of decreasing energy. Yes or no? Yes or no? Yes or no? So if flow is taking place between 1 and 2, you add like this: energy at 1, energy means your Bernoulli equation. P1 by rho g plus V1 squared by 2g plus Z1 is equal to E2 plus head loss, that is HF. If flow is from 1 to 2. If flow is from 2 to 1, if flow is from 2 to 1, it will be like this: E1 plus HF is equal to E2. Understood beta or not? Understood beta or not? Because if flow is taking place from 1 to 2, if flow is taking place from 1 to 2, if flow is taking place from 1 to 2, your energy, your E2 must be less than E1. Getting my point or not? If flow is taking place from 2 to 1, from 2 to 1, your energy at 1 must be less than energy at 2. Understood, beta? This way can also be used now, as we have mentioned it also. So this way can also be used in order to find the direction of the flow. Sometimes we are asked to find the direction of the flow, so we can use this concept to find the direction of flow as well. Now coming back to the formula sheet, now this is a very important Darcy-Weisbach equation. Okay, so see, many question you will see in the previous year GATE examination, that if velocity is increasing by double, if velocity become double, what will happen to this head loss? Mostly this equation is used while in the questions of the pipe flow you see. Okay, now there is a very big confusion in a student, that's we usually see this formula, because many of us are using the book name as very good book, R.K. Bansal. In that set, this formula is given. In that set, this formula is given. So mind my words, do not use this formula unless F is given to be friction factor. Sorry, friction, coefficient of friction. So if they are saying that coefficient of friction value is there, if they are saying coefficient of friction, if they are saying coefficient of friction, then you may use this formula. Now, when to use this formula? So in questions, they just give the value of F like this. If they have written like this, that F is 0.04, use this formula, beta. Use this formula, do not use this formula. Understood or not, beta? Understood or not? Understood or not? So in this formula, we know F is our friction factor. In this C, it is coefficient of friction in this formula. So here the F is friction factor. In this formula, the F is beta our friction factor. Understood or not? F is friction factor. So if nothing is given, you consider your F to be friction factor. If nothing is given, you consider your F to be friction factor. Understood, beta? Understood? You might have seen this equation multiple times. Now I want you to solve a question on the basis of this equation. Please see this question. Let's try and solve this question. Please try and solve this question, please. Please see this question and try to solve it. We must be using this HF. All of us must have memorized this formula also, because in this school boosting session, I am considering that we already have completed the fluid mechanics. Now we are trying to revise the concept. We are trying to see the key points so that we can revise the fluid mechanics before the examination, a day or 2 days before. Yes or no? Yes or no? This is the purpose now, beta. This is the purpose now. Now let's try to solve this question. Yes, length is 10 meter, beta. I have skipped the unit here. The length is 10 meter, beta. 10 meter. My mistake. It is 10 meter. 10 meter. Understood or not? Please try to solve this question. Please see this question. Let's try to solve this question. Let's try to solve this question, beta. Let's see if you can solve it. I'll give you 2-3 minutes to solve this question. Let's see if live students can solve this question. Let's see if we can do it. Now, meanwhile, I request you guys to like, share, and subscribe the GATE Academy. If you feel that the sessions we are doing is useful to you, is helping you in a way, we are trying very hard to make you successful, make your preparation successful. No, Sujit, answer is not correct, beta. Answer is not correct. Please do subscribe. Please do subscribe. If you have not subscribed it till now, please do subscribe the GATE Academy channel. No delete. No delete. So see, again, let me describe this question. Let me give you some hints in this question. Okay. As I said, my purpose is not to make you solve the question, not to do the calculation and all. I don't want to waste your time. Okay. We want to utilize this session, score booster session. We want to cover as much as ground as possible. Okay. Now, in this, what they are saying, water flows through a pipeline whose diameter varies from 20 centimeter to 10 centimeter to 10 centimeter in a length of 10 meters. So the length is given to be 10 meter. The length is given to be 10 meter. The head loss in friction. So they are asking you HF, head loss in friction. So we just have seen the formula FL V square by 2GD. FL V square by 2GD. Getting my point or not? Getting my point or not, beta? Getting my point or not? Now, in this question, since the you can say since that diameter is varying continuously from 20 to 10, the diameter is varying continuously from 20 to 10. Now, I always give you this statement that whenever you see something varying, you must make arrangement of integration. Do I say it or not, beta? Always do I say it or not? How will you be able to recognize that in some question we have to do the integration? I told you this in the previous score booster session also. In the previous score booster session also, I told you this. That whenever something is in variation, you need to make arrangement for the integration. So for making the arrangement of integration, we need to take a strip. Yes or no? Let's say this strip distance is dx. This strip distance is dx. Yes or no? Yes or no? Yes or no? Now, if this strip is distance is dx, so let me see what is the head loss due to friction. What is the head loss due to friction? What is the head loss due to friction in this dx strip? So it will be, sir, fv square dx fv square dx upon 2gd. Yes or no? Yes or no? Yes or no? Please tell me yes or no. Now, please tell me one more thing, sir. This V is also a function of X, and this diameter also we are seeing that it is like a function of X. Now, if we write this equation, like this, we somewhat know that these are constant, and we need to differentiate it between 0 to L, that is 0 to 10, we need to integrate this. Between 0 to 10. Yes or no? See, once you have written an equation like this, what else you can do? What else you can do other than integration? What else we can do other than integration? So somehow we come to know that we have to integrate. Now, something of common sense I am telling you. Now, please tell me, this is dx, this is dx. So this should be in the form of x or not? Okay, this is 20 to 10, my mistake. If you write 20 to 10 also, 0 to 10 also, these are the same thing only. No problem. 20 to 10 we can integrate. Yes or no? No, 20. Why 20 to 10? We are integrating with respect to Madhu Vismata. You are confusing me. See, this dx is length na. Beta. Yes or no? Shantanu. You are also saying, sir, why 0 to 10? Dx is length na or not? Dx is length na. So we need to put the limits of the length or diameter. So the length is changing from 0 to 10 or not? If I say this x, the limit of this length is from 0 to 10 or not, beta? So that is why I am putting 0 to 10. Understood or not, beta? Understood or not? Understood or not? Tell me. Tell me. Tell me. Okay. Now this DHF, DHF is F by 2G. Now, did you understand this point that, sir, we need to convert it? We need to convert these V and D in terms of X so that we can integrate. Yes or no? Yes or no? Now we know that how we can do it. So how we can do it? We can use Q is equal to area into velocity. Yes or no? So in place of V, I am putting Q square upon pi by 4D square. Now, discharge is constant or not? Say yes or no. Say yes or no. Say yes or no. And this is also a square. Discharge is constant or not? So now from this equation, can I write like this? DHF is equal to F by 2G Q square upon pi by 4 whole of a square, and it will become 0 to 10 1 upon d to the power 5 dx. Yes or no, beta? Say yes or no, beta? Say yes or no, beta? Say yes or no, beta? Yes or no, beta? And tell me now, yaar, all of you, please tell me now. Please tell me now. All of you. Now, sir, now if I can write d as a function of x, if I can write d as a function of x, if I can write d as a function of x, I will be able to integrate it, and all other values are given in the question. See, f is given in the question, friction factor is given in the question, discharge is given in the question. Yes or no? Yes or no? So if we can find the function of d, you are saying, sir, Delhi, why d power 2? Beta, this is v square na, this is v square na. So if you are replacing v square, so it will be q square upon a square, and a is pi by 4 d whole of a square, pi by 4 d square whole of a square. And area is pi by 4 d square or not? So if you are squaring it, it will be d to the power 4 or not? Please tell me. Delete. 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 Please tell me, beta. So all of us now understand this. All of us now understand this. That's that if we can write this d, if we can write this d in terms of x, if we can write this d in terms of x, in terms of x, if we can write this d in terms of x, our question will be solved. Our question will be solved. So if I say this is x, this is L, and the diameter is uniformly changing, diameter is changing with uniform variation. So you know a general rule? So if it is d, so how to write d in terms of x? So how to write d in terms of x? Do you know it? Do you know it? If you not know it, just know it now. So d can be written as d1 minus d1 minus d1 minus d2 by L into x. Getting my point or not? This is the general equation. Are you know this equation or not? This is the general rule, na beta. This is the general rule, na beta. If something is varying from one place to another, something is varying between some distances like that, we can use the general equation or not? Say yes or no, beta. Say yes or no. Say yes or no. Slope of the line, yes. Yes or no? अरे tell me ना यार. Tell me now. So if I put all the values here, so I believe now you can do this question. 20 minus 10 upon 10 into x. Yes or no? Yes or no, beta? Yes or no, beta? Yes or no, beta? So it will come out to be 20 minus x. Yes, Shantanu, this can come directly in 2 marks question. In this only thing, in the C, HF is equal to FLV squared 2GD, all of us know. In this, there is a twist that you have to apply the concept of integration. And let me tell you one thing, in GATE examination, they have this fun that they do this kind of a question in which you know everything. You know all the formulas, you know all the concept, but still you have to apply some aptitude of yours. That is why the examination is called Graduate Aptitude Test of Engineering, because this examination also checks your aptitude. Getting my point or not, beta? Getting my point or not, beta? Getting my point or not, beta? Please tell me, getting my point or not? Understood? Now you have this variation. Now can we put this d? can we put this D back in equation number 1 and then can we integrate or not? Can we integrate or not then? Yes or no? Yes or no? Please tell me yes or no. Is it clear or not clear? Please tell me, beta. Please tell me, beta, is this clear or not? Is this clear or not? Now, can I say that you can put it back in equation number 1 and you can integrate? Yes or no? Yes or no? So when you are going to integrate it, you will be getting H is equal to 0.968 meter. 0.968 meter. This is the final answer. So you may cross check it. You may cross check it also. All right? All right, beta? Now on this formula sheet, can we tick this also? On this formula sheet, can we have a tick here? Yes or no? Yes or no? Yes or no? Is this formula understood to everyone or not, beta? HF formula, head loss due to friction. Simple questions we can do. Yes or no? Yes or no? This was question that I have given to you. It was a little bit twisted. All right. Now moving ahead in this pipe flow topic. So we have some minor losses also. We have some minor losses also. Okay. So minor losses, I have mentioned the formula here. So minor losses. So normally, see, normally if these are not mentioned, that it is not mentioned in the question that consider the minor losses, you need not to use them. You need not to use them. Getting my point? You need not to use them. Okay. Okay. But if you are deliberately asked to find this, so you can have a look at these formulas. Okay. So this sudden expansion. So sudden expansion means, okay, quick revision. Sudden expansion means that your area is increasing suddenly. So the changes of velocity are happening. When the changes of velocity are happening suddenly, we have some losses. That is called as sudden expansion. Similarly, sudden contraction like this, like this. So from a bigger area, if your fluid is bound to go into some smaller area, again there will be abrupt changes of velocity, or whenever there is abrupt changes of velocity, we have some losses. So this is the loss due to sudden contraction. Entry loss is this, exit loss is this, exit loss is this. So this is something that could be asked, which is not getting very frequently asked in the examination. Yes or no? Yes or no? Is this understood or not? Can I place a tick on this minor losses as well? Yes or no? Yes or no? Just a quick revision of formulas of it. Yes or no? Now, one more thing they ask is about the power transmission through pipe. What more they are asking about this? What more they are asking about? What else, beta, they are asking about? So they are asking sometimes about the power transmission through pipe. Power transmission through pipe. So how to get the power transmission through pipe? By using this formula. By using this formula. Getting it or not? By using this formula, that is rho GQH net. That is rho GQH net. What is this? What is this? So this is nothing but mgh m dot gh. Yes or no? Yes or no? The potential energy. Yes or no? Sir, what is this H net, sir? So we have some pipe like this. So let's say we have some fluid here. We have some fluid here, and this fluid is coming out from here and exerting some pressure. This fluid is coming out from here and exerting some pressure. So if it is H, if this is H, if this is H, so what will be your H net? What will be your H net? So H net will be H minus the power or the head that has been lost during the flow in this pipe. Getting it or not, beta? So this is your H net. So you have to calculate your HF by using the same formula, and you can place it here. You can place it here. Getting it or not? Say yes or no, beta. Say yes or no. Can I place a tick here? Can I place a tick here? Yes or no? Live student, please respond. Please tell me, can we do it like this or not? Please tell me, beta. Please tell me, beta. In this, the frequent question that is getting asked in the examination is about the condition of maximum power. Yes or no? You might have seen it also. Yes or no? So if we derive the condition of maximum power, so if H is equal to HF by 3, if H is equal to HF by 3, this is going to be your condition of maximum power. This will be your condition to maximum power. Understood or not, beta? Okay, all right. So now can we place a tick here also on this pipe flow? Yes or no, beta? Yes or no, beta? Okay, okay, okay. Now the next is our vortex motion. Next is our vortex motion. Okay, vortex motion. So in vortex motion, beta, what happens? In vortex motion, what happens that your fluid follows a circular path. Yes or no? It follows a path like this. It follows a path like this. Getting my point or not? It is being rotated. It is being rotated. So in a vortex motion, whenever the fluid is having bulk molecular rotation, we call it vortex motion. We know it. We know it. So see, sir, this is very importantly, gives you the pressure variation with respect to the radius. The pressure variation with respect to the radius. Getting my point or not? Getting my point or not? Say yes or no. Say yes or no. Say yes or no. Okay. We already have seen this. So in general, in a static fluid, what we have seen in static fluid, what we have seen that pressure varies with depth, isn't it? Yes or no? Pressure varies with depth. Okay. Okay. So in that, if at certain jet, if at certain jet we required to find, if at certain jet we were supposed to find the pressure, we could use this equation. But in vortex motion, pressure also varies with the radius. Pressure also varies with the radius. So since the pressure is having a variation with the radius, so this 3.1 equation shows you the variation of pressure that take place with respect to the radius. Yes or no, beta? So if we combine these two equations, we get the generalized force vortex equation which combinedly is giving you the change of pressure with respect to the radius as well as the height. Radius as well as the height. So where to use this equation? Where to use this equation when you have to find the pressure difference with respect to datum, with respect to jet? Where to use this equation, beta? Where to use this equation? We can use this equation where we have to find the variation with respect to radius. And in this question, beta, in this where to use this equation when we have to find the variation of pressure with respect to both radius and datum. With respect to both radius and datum. Now I have written it in red. What does that mean, beta? I have written it in red. What does that mean, beta? What does that mean? What does that mean? I have written it in red. So it means that it is very important. Yes or no? It is very important. So in the vortex motion, mostly you will see this formula is getting used. This formula is getting used. Now, sir, what is this jet, sir? Certainly, sir, Z is representing some height. Certainly, Z is representing some height. And this is valid for force vortex motion. This formula is valid for force vortex motion. So if we have a container, if we have a container like this, if we have the container like this, if we have the container like this, what we can do, if we are putting some shaft into it, and if we are making it rotated, how to use what is the use of this formula? Please see, let's see the concept behind it. So we have a container like this. If we have a container like this, and we are rotating, and this is, let's say, filled with water up to some height, it is filled with water, and we have given some rotation omega through something, through a shaft, through a propeller, through anything, okay, through a stirrer. So if we have given some omega to this shaft, the liquid inside the container will displace, and will be in a shape like this, will form a shape like this. Getting my point or not? Will form a shape like this. So this geometry that you see between A, B, and C, this A, B, and C is a paraboloid. Geometrically, we call it a paraboloid, and this is the jet we are talking about. This is the jet that we are talking about. That is the height of this parabola. So the volume, if we talk volume of paraboloid, so we all know, we might have known that the volume of paraboloid is half the circumscribed cylinder, yani half pi r square z by 2, where r is the radius of it. So how to find the volume of paraboloid? Is that clear? Yes or no? Yes or no? Yes or no? So if some container is like this, and this is your jet, so if this is A, B, and C, so volume of ABC will be pi r square Z by 2. Ali, it is not clear, beta. Let's clarify it. Let's further clarify it. So this volume of paraboloid, beta, this is geometry. Okay. So if we want to find the volume of some paraboloid, beta, what we need to do? We need to enclose it by a cylinder. So if I want to find the volume of this black paraboloid, so I have enclosed it with cylinder of radius r and height z. So the volume of this paraboloid, will be half the volume of circumscribed cylinder. So on this parabola, what is this circumscribed cylinder? It is pi r square z, and we have to divide it by 2. So this is your volume of parabola. Getting my point or not, beta? Understood or not, beta? Now, okay, understood. Now all we have to do is applying these concepts rightly. All we want to do is to apply these concepts rightly. So now I am going to show you a question. let's try to solve this question, and let's see how to apply this concept. How to apply this concept. Please attempt this question. I want you to attempt the both of the parts. I want you to attempt both of the parts. Can we attempt it? Can we try to do it? So whenever I always give you this tip that in this subject or in any subject, whenever you are solving some question, please try to draw the diagram or figure of it. The things will be in front of you. You will be able to recognize smoothly which formula is to be used and what. Getting it or not, beta? Getting it or not? What is the answer to these questions? Can you please solve this? What is the answer to the first part? So if I try to draw a figure, if I try to draw a figure of it, so a cylindrical vessel of 12 centimeter diameter is given. So let's make a cylindrical vessel. It is of 12 centimeter in diameter and 30 centimeter deep. So this is 30 centimeter deep. Beta Shantanu, it is not asked. Some of them are asked. Okay, from the concept of these, you can see the question in which this 3.1, 3.2, 3.3 is getting used. But the concept that I am going to show you now is not asked till now, but certainly it can be asked. Certainly it can be asked. Getting my point? Getting my point? Now, if I draw this figure, so this cylindrical vessel, this is 12 centimeter, this is 30 centimeter, so this will be 6 centimeter. Now, it's filled with water. Now, it is getting rotated at 300 RPM. Now, what I told you, once it gets rotated, it will form a paraboloid. Now, please listen to me. The score boosting, this is a score boosting session. So in this, always remember in force vortex motion, the geometry which is formed is always a paraboloid. There is no exception to it. Yes or no? There is no exception to it. Always a paraboloid will be formed. Okay? A geometry like a paraboloid will be formed. Okay? Okay? Thank you, Vijay. This is for what we are trying to do now. This is what I am trying to do. Okay. See, in 6 hours, it is impossible to cover everything in the fluid mechanics. Okay. What we are trying to do, as I said repetitively, that sir, we are trying to quick revise all the concept, all the formulas we have seen. So we can have a quick revision of this whole subject. Okay. Now this is Z. Now the first step that we can do is find the Z. So R omega is square by 2G. R omega is square by 2G. So in the first case, if you find it, In the first case, if we find it, so we will be getting, this will be 6 square, this will be 2 pi into 300 by 60 whole of square divided by 2 into 9.81 divided by 2 into 9.81. So if we find it, if we try to find it, what we are getting? Can somebody please tell me? Can somebody please tell me? So we are going to get 18. Since we are using this 6 into centimeter, we will be using this also in centimeter. So we will be getting 18 centimeter, that Z is 18 centimeter. Now what they are writing here, that find the quantity of liquid left in the vessel. What is the find the quantity of the liquid left in the vessel? So what is the quantity of the liquid left in the vessel? What is the quantity of the liquid left in the vessel? So quantity of the liquid left in the vessel, can I say from this geometry, can I say liquid left in the vessel? So the liquid volume of liquid left in the vessel, so it is the volume of cylinder. It is the volume of cylinder minus volume of parabolite formed. Yes or no? Yes or no? Yes or no? So what is the volume of cylinder cell? So it is pi r square h. And what is the volume of this parabolite? Pi r square z by 2. So we'll be able to find the volume of liquid left in the container. Say yes or no, beta. Say yes or no, all of you. Is this first part is clear or not? First part is clear or not? First part is clear or not? Please tell me. Please tell me, is this first part clear or not? Please tell me, beta. Please tell me, beta. Yes or no? I'm seeing your chest, beta. All right. Now, if we start doing this second part of this question, if we start doing the second part of question, so again, let's follow the same procedure, beta. Let's follow the same procedure. So if we now follow the same procedure, the first step we do is finding the jet. So this is r square omega square. This is r square omega square by 2g. This is r square omega square by 2g. So this is 6 square. Now you have to do 2 pi n. So n here is 600 by 60 whole of square by 2 into 981. So if you do like this, you will be getting Z is equal to 72 centimeter. Z is equal to 72 centimeter. Now the question, now the thing that will come into your mind is that, sir, this is 30 centimeter, this is 72 centimeter. Now remember this, you always follow the procedure what you learn. You always follow the procedure what you learn. So what I said, parabola is always formed. So let's try to form the parabola. So if a parabola is formed, it would be formed like this. It will try to form a parabola. So this portion which I have represented by this dash line, wouldn't be completed. Yes or no? It will be like this. Yes or no? So this is your 72 centimeter. So what is now the liquid left in the container? So this highlighted region is the liquid left in the region. This highlighted portion is the liquid left in the container? Yes or no, beta? Please tell me yes or no. This highlighted region will be the amount of liquid that is left in the container. So if I call it A, B, C, D, E, F, G, Now, all you have to do, now this question is no more of fluid mechanics, but of aptitude. But of aptitude. Now you have to find this highlighted area, highlighted volume, how to do it, how to do it. So we will follow the procedure. So what we have seen, how we have done the previous problem, the first part of this problem. So liquid left in the container is volume of cylinder, is the volume of cylinder minus volume of parabolite, volume of parabolite. This is what we do, the volume of parabolite. But here, if we see the parabolite ACGDF, ACGDF. So if we subtract, now please listen to me very, very carefully. Please listen very, very carefully. So if we are subtracting the volume of this whole parabolite, are we subtracting this extra? This reason we are subtracting for extra? Say yes or no. Say yes or no. Say yes or no. If we subtract the volume of parabolite ACGDF, so isn't it that we are subtracting this part extra? So if we are subtracting this part extra, how can we balance the situation that we can add it? We can add it, and this is again looking like a parabola. So this is again a parabolite. We can add this parabolite. We can add the volume of parabolite CDG. Tell me, is this understood or not? Please tell me yes or no. Is this understood or not? To everyone. Is this understood or not to everyone? Please tell me, beta. Please tell me, beta. All right. Now, sir, volume of cylinder. Now, volume of cylinder, sir, we know it is pi r square h. Volume of this parabolite is, sir, pi r square 72/2. Now, sir, if we want to find this volume of this green highlighted parabolite, what we require, sir? We require pi. We require the radius of it. We also require, sir, this r. We also require, sir, this r. And we require this Z1. We require this Z1. So the Z1 is, we have the Z1 we can have. So let's call it a small r. So Z1 we have, that is 42. 42. So this capital R will we have 6 centimeter. This H we have, everything will we have except this R. Except this R. Now, sir, how to find this R? How to find this small r? So this small r is, we know this equation or not? From this equation, how to use this equation? How to use this equation? I am trying to tell you that. I am trying to tell you that, beta. And most of the students and teachers do not cover it. Do not cover this portion. That is why deliberately I have put it into this score booster session. Getting my point or not, beta? Because this is something that can be certainly asked here. All right. Now we have the Z1. We have the Z1. We have this omega. We can find this R. We can place it back here. We can place it back here. So once we can place it back here, we will have our answer. Say yes or no, beta. Say yes or no. Say yes or no. So the final answer of this B part will be somewhere near 702 centimeter cube. You can cross check it. Any doubt in this question, beta? Any doubt in this question? Can I place a tick on this vortex motion also? Can I place a tick on this vortex motion also, beta? Tell me. Tell me. Yeah, somewhere Rajput near 700, as you are telling me, 698. Now, is this vortex motion is clear to all of you, beta? Is this vortex motion clear to all of you, beta? Yes or no? Yes or no, beta? All right. Now compressible flow topic we already have discussed. In a separate video. You can see that video. Where to see it, beta? Where to see it? You have to subscribe the GATE Academy channel, as I keep telling you. So you subscribe the GATE Academy channel. We had a series named as Steam and Gas Turbine, which is newly added syllabus to GATE 2021. So in that series, we have completed the compressible flow also in English. Okay. On the Hindi channel, you can see it by a name of compressible flow. You can take a look at that. It will be clear to you. It will be clear to you. So the only score boosting tip I want to give in this compressible flow, see, only remember this formula, Mach number. Only remember the formula of Mach number. And please read this note. Please read this note. What is this note? Memorize nothing else. I have written, beta, memorize nothing else. Do everything from the basic equations of thermodynamics, Euler equation, and continuity equation. Euler equation and continuity equation. Getting my point or not? Okay, so in compressible flow, if you start, this is a tip, beta. This is a newly added syllabus in GATE 2021. Previously, it was not there. So we have no hint which kind of question that could be asked in compressible flow in your GATE 2021 examination. But if we take the reference of Indian Space Research Organization paper, there mostly the questions are asked on the basis of Mach number. On the basis of Mach number. So what I recommend you that you do not memorize any other formula in this compressible flow. You just memorize the formula of this Mach number. You just memorize the formula of this Mach number and do the rest of thing by using your basic equation that we learned in thermodynamics, like ideal gas equation, like Bernoulli equation, like adiabatic property equation, isothermal equation. Okay, things will be done. There is nothing to memorize in this compressible flow. Okay, is that fine or not, beta? Is that fine or not? Are we going to prepare the compressible flow or not? So when we are going to prepare it, I recommend you go and watch. I only have taught. Okay, go and watch the compressible flow. In the English channel, it is in the name of steam and gas turbine. In the Hindi channel, it is in the name of compressible flow. You can refer any of them. Okay. Okay. Now moving to the next topic, that is boundary layer theory. So we have completed up to this 3 portions. Now we are trying to cover boundary layer theory, dimensional analysis, laminar flow. So these topics are formula based topic. What kind of a topic? Mostly formula based topic. Okay. Okay, these topics are mostly formula based topic in which if you remember the formula, you will be able to do it. If you do not remember the formula, you won't be able to do it. Simple as that. Simple as that. So let's have a quick revision of them. So in boundary layer theory, Shantanu, I will upload it. So you please subscribe the GATE Academy channel. Okay, you will be having this formula sheet. Okay, it will be uploaded. All right, it will be uploaded. Now, beta, moving to the next topic, this boundary layer theory. So as I said, that this is mostly a formula based topic. So if you see, first thing that is very important in this boundary layer theory is seeing the Reynolds number. So I am briefly trying to make you revise the concept you have learned in boundary layer theory. I am briefly trying to make you remember the formula you have learned, remember the concept we have learned in boundary layer theory. So the first thing that you have to do is finding the Reynolds number. Once you find the Reynolds number, beta, once you find the Reynolds number, please check this, that whether the Reynolds number is less than 5 into 10 to the power 5 or not, whether the Reynolds number is less than 5 into 10 to the power 5 or not. So if it is less than 5 into 10 to the power 5, we remember that the flow is laminar. If it is greater than 5 into 10 to the power 5, we may remember that then the main flow will be turbulent. So this is the case one we are talking. So in case one, when Reynolds number is less than 5 into 10 to the power 5, means the flow is laminar. So when the flow is laminar, now listen to me very, very carefully. When the flow is laminar and you have not given any velocity profile. So if you remember what we learned in boundary layer theory, so in boundary layer theory, we have a boundary layer region which is created due to the variation of velocity, due to some distribution, due to some variation of velocity in the boundary layer region. So please remember, if no velocity profile is given in the question, you will see the kind of question in which no velocity profile is given. So if no velocity profile is given, you consider these formulas by using Blasius solution. So this is your formula. Very importantly, you will see multiply getting used. So this is the formula of boundary layer thickness, beta. This is the formula of boundary layer thickness. All right, beta. This is the formula of boundary layer thickness. Okay, boundary layer thickness. So see, while using this formula, please be careful about the Reynolds number. So this Reynolds, see, this is the common mistake. See, we have to memorize this formula, but when we are memorizing this formula or any other formula in this subject or any subject, please do understand how to use that formula. If you want to do your questions right, please do understand how to use that formula. Okay, now in this formula, the common silly mistake we guys do is about this Reynolds number. That we usually are using this Reynolds number. What we have calculated in the beginning of the question, but it is not. See, let me explain this formula to you guys. So if there is a plate, beta, so what is your boundary layer thickness? So boundary layer thickness formula, we can use this when no profile is given, when no velocity profile is given. So when no velocity profile is given, beta, so we can consider this to be your boundary layer thickness. So beta, this x, let's say this is 1 meter. Let's say this is 1 meter. So we can find this boundary layer. This is your boundary layer thickness, beta. So this is your boundary layer thickness. So we can find this boundary layer thickness at any x. If I am taking the x from here, yes or no, beta? We can find this boundary layer thickness at any x from this leading edge, yes or no? From this edge, please tell me yes or no. Yes or no? Now, if I have to find this delta 1, so I have to place, remember this, I have to place x1 here, beta. I have to place x1 here. And in place of Reynolds number, when I am using the formula, I have to put x1. I have to put x1. I have to put this x1 beta. Okay, so this Reynolds number will also be changed. This Reynolds number will also be changed according to the location at which you are asked about your boundary layer thickness. According to the location at which you are asked about your boundary layer thickness. I have mentioned it here also because this is something I feel that people make mistakes. So I have mentioned it in the formula sheet that if x is equal to 1, this is, if x is equal to 0.5, this is beta. This is the thing you have to use. Understood? Understood? Yes or no? Understood? Now, in this chapter, what else they are asking you? They are asking you about this drag force. They are asking you about this drag force. So this drag force, this is the general formula. This is the general formula of the drag force. Half CD rho A U infinity square. So again, if no profile is given, all the formulas that I have written, and we are talking about the laminar flow, we are talking about the laminar flow, we are talking about the laminar flow. So when we are talking about this laminar flow, we need to use the Blasius solution. We need to use the Blasius solution. So these formulas are of the Blasius solution. Getting my point, beta? Now in this formula, when we are finding the force, always remember force is an average concept. So the score boosting tip is always use average drag coefficient while calculating the drag force. And when we are calculating the average drag force on the plate, we are considering the Reynolds number of that length. That is why I have put it equal to L. Getting my point or not? So in order to find the CD, in order to find the force on the plate, you need to use this R. You need to use this Reynolds number. Understood or not, beta? Yes, Mahadev, we have turbulent flow in the syllabus, but the questions are not frequent. So I have not written the formulas of the turbulent flow in this sheet. In this, I tried to put the important formulas, important concepts. So we can do it ourselves. Okay. So in the drag force, when we are calculating the drag force, this CD, if no profile is given, we can comfortably use this formula 1.328 by root REL. Yes or no? Similarly, if we have to find the shear stress, so I always keep telling you guys that stress is a localized phenomena. So when it is a localized phenomena, it is always at some point. So since it is a localized phenomena, we need to use local drag coefficient. What coefficient? Local drag coefficient, beta. Local drag coefficient we need to use. Okay, and this local drag coefficient is half of the average drag coefficient, that is 0.664 upon root REX. So if you see, since it is a localized phenomena, so it is a localized phenomena means stresses are always at point. So if we are asked the shear stress at the middle of plate, so we have to put x is equal to L by 2 on in the Reynolds number. If we are asked x is equal to L by 4, so again, since this shear stress is at point, so with the changes of point, when the point changes, the shear stress also changes, and when the point changes, the x also changes. So we have to use the corresponding x. Say yes or no. Say yes or no. So these formula that I have written here is for turbulent flow boundary layer. So these are the boundary layer formulas. So again beta, again if no profile is given, we can use these formulas. We can use these formulas for turbulent flow. Understood or not beta? Understood or not? Understood or not? So boundary layer theory is quickly revised. As I said, these topics are mostly formula based. So what we can do, since we have some shortage of time as well, so what we can do, we can do some questions, we can do some questions ourselves. Yes or no? Yes or no, beta? Can we do it? Can we do it, beta? Yes or no? Yes or no? These are just simple formula based. Okay? Just take note of the point I told you. You may make mistakes in them. Understood or not? Can we move ahead? Can we move ahead? Please tell me, can we move ahead? Please tell me. Good evening, Subodh. All right, all right. So this is your boundary layer in turbulent flow. So Subodh, what I tried to say that this boundary layer theory. So all the formulas we have mentioned here, these formulas, we need to be careful about this x. Okay. So when we are finding the boundary layer thickness, finding the boundary layer thickness, we need to see at which x we are asked. If no x is given in the question, if it is not mentioned that at what point you need to calculate your boundary layer thickness, you just consider the maximum boundary layer thickness which is created at the end, of it. Understood? Similarly, these formulas we can use when no profile is given. And for turbulent flow, when we know the flow is turbulent, so when Reynolds number is greater than 5 into 10 to the power 5, the flow is turbulent. Understood, beta? Now moving ahead in the next topic, in dimensional analysis, again it is formula based. So in this dimensional analysis, we need to memorize the formula of Reynolds number. So what is this Reynolds number, beta? Reynolds number is ratio of inertia force to viscous force. So the formula of Reynolds number we already have mentioned, rho VL by mu. Similarly, another number is Frown number. Frown number is the ratio of inertia to gravity force. But as Subodh, coefficient of drag, the physical significance you are talking about. So higher the coefficient of drag, higher will be the resistance. Drag force is the force we need to overcome in order to move somebody. Okay. So higher the coefficient of drag, beta, higher will be the resisting force. All right. Now this Frown number is your ratio of inertia force to gravity force. We have to, if we derive the formula of it, it will be V upon root Lg. Okay, it will be V upon root Lg. Similarly, we have this Euler number. This is the formula of Euler number, beta. This is the formula of Euler number. Okay, very simply, dimensional. We all know this formulas or not? Dimensionless number, Reynolds number, Frown number, Euler number. Yes or no? There is one Newton number also, that is opposite of Euler number, reciprocal of Euler number. Getting it? Similarly, we have Weber number. So Weber number is the relation of inertia force to surface tension force. When inertia force is related with surface tension force, yes, these are non-dimensional quantities which we are using in modeling. So this is the formula of this Weber number. Okay. So if sufficient data is given, I think there is no need of a Mach number I already have mentioned. Okay. So if necessary data is given, we can certainly find this dimensionless numbers. So dimensionless number. So I hope this is also clear to you. So can I place a tick on these two topics also? We are not able to solve a question of it, but we have quickly revised the formula sheet of it. Yes or no? Yes or no? So both these dimensionless numbers are used in modeling. Getting my point? So if it is a Froude model we use in the designing of spillways. Okay. So a spillway is such a large thing that you cannot make a model of it. Okay. Okay. So you make a short scale model, a small scale model of it. Then you do the testing on that model. Beta. And that result you transfer to the actual prototype. Understood, beta? Understood. Now, let's quickly see the formulas in laminar flow. So laminar flow, I want to make you solve a question of laminar flow. So laminar flow in pipes. So if laminar flow is taking place in pipes, and when we say the laminar flow is taking place in the pipe, when the Reynolds number is less than 2000 beta. When the Reynolds number is less than 2000. Is less than what beta? It is less than 2000. All right. Just a moment, beta. Just a moment. All right. So in this, Mahendra, turbo machinery, we are not able to do beta in this score booster session. Okay. We can think of some separate session for that. Okay. You may subscribe the GATE Academy channel. Okay. There we can see if we want to do, if we can do it. Okay. Okay. So what is the purpose of this score booster session? We all know in 6 hours, nobody can teach fluid mechanics. All I'm trying to make you revise the formulas, the revise of concepts. Mahadev, it is impossible to tell like that. Because so both stream function, potential function, we have discussed in previous score booster session, beta. You may refer them. This is the last score booster session, and we are left with 5 minutes only. Understood? Understood, beta? Okay. Okay. So we have, this is our third score booster session. Okay, now let's quickly see the laminar flow in pipes. So as I was talking about, Mahendra, I was talking about this fluid machinery. So fluid machinery itself is a topic. It is not a subject. It is subject in the semester, but in GATE it is a topic only. Now you are asking what is important topic in fluid machinery. So it itself is a topic. Then what will be important topic in it? Understood, beta? Understood, beta? Okay. If you are a student of the GATE Academy, you can see the recording of it on your LMS account. I myself have taught fluid machinery in 4 hours, 5 hours. I have completed it. So if you are the GATE Academy student, you may see the recording of that also. All right. Now coming to it, let me quickly discuss these formulas. So when we talk about this laminar flow, so it happens in case of pipes. There are two distinct formula for it. Two different formulas are there for it, beta. Two different things we have to see. One is for pipes. Remember, one is for pipes, beta. One is for pipes. So both we can visualize the displacement thickness. It is, yeah, Vijay, it is a little bit difficult, but what we are doing, we are trying to do it, beta. So just listen to me. Very simple. So in laminar flow, we require this 8 formulas. 4 for pipe case, 4 for pipe case, and 4 in plate cases. 4 in pipe case, 4 in plate cases. Thank you, Vijay. Delete it. They are there. I myself have taught, beta. I myself have taught. All right. Now, in case in each of these pipes and plates, in each of these pipes and plate, beta, we have these 4 formulas: shear stress. So this is the formula of shear stress. Okay. So what this formula is? So this is your R. So if it is a pipe, let's take 5 more minutes. So it is a pipe, beta. It is a pipe. It is a pipe. All right. It is a pipe. So this formula is giving you the variation of shear stress with R. With R. Okay. Similarly, this formula is giving you the variation of velocity with R. Okay. Okay. So from this equation, if you see, beta, your maximum velocity and average velocity are both different. So this is the third thing and very important. This is the most important. So in laminar flow, beta, the ratio of maximum velocity and average velocity is 2. And always remember, sir, we are very much using this formula. Na? Discharge is equal to area into velocity, beta. Yes or no? Yes or no? Yes or no? So remember that in finding the discharge, you are using mean velocity. You have to use mean velocity. So if maximum velocity is given to you, so we cannot discuss it, beta. Axial and radial flow, we cannot discuss it now, beta, because of the constraint of the time. Okay. So this discharge is area into average velocity. Always remember. So if you are given in the question maximum velocity in case of a pipe, do remember to divide it by 2 so that it will become mean velocity. Getting my point? Okay. Now the last is pressure difference. The pressure head difference. So this is given by this formula. Very useful formula. In the pipe flow topic, we have seen this formula. Na? HF is equal to FL V square by 2GD. FL V square by 2GD. Yes or no? Yes or no, beta? So in some cases we are not given with this F. In some cases we are not given with this F. Getting my point? Okay. So if you relate it, your F will come out to be this. Very useful, beta. Very useful. So your friction factor sometimes is not directly given. Your friction factor is sometimes not directly given in the questions. So in that case, beta, you can find your friction factor. By using this Reynolds number. Now, please do this question. This will be the last question of this session. This is code booster session. I want you to do it. And if you do not have memorized the formula yet, I am giving you the formula as well. You have to memorize all these formulas. Now please do this question. Let's see if we can do this by using this formula. So in this question, beta, formula also I have mentioned on the screen. Now let's see, even the formula is given to you, will you be able to do it or not? Let's see. Subodh, this is the question. This is the question that is given. So if Subodh beta, if this question is getting asked in the GATE examination and this much only is written, this much only is written, this much only is written in the question, who will you ask that give us the diagram? We have to manage from it. Na? Vijay, you are giving me some answer, beta. I don't know if it is correct or not. I don't know if it is correct or not. I want all of you to attempt this. Okay, we'll take 2 minutes to attempt it. We'll take 2 minutes to 2 minutes to attempt this. So your answer is incorrect, beta Vijay. Your answer is not correct, beta. So I hope all of you have liked the session. Is this session useful to you guys or not, beta? Have you find these sessions, score boosting sessions of fluid mechanics useful or not? Please tell me. Please give me your feedback, beta. I tried to cover as much ground in this duration. Okay, and the purpose of this score booster sessions is to make you quickly revise the concept of the fluid mechanics, to make you quickly understand that how and what cares that needed to be taken while using some of the formulas. All right, all right. The formula sheet here will be shared with you guys. For that, please subscribe, like, and share the GATE Academy channels. Thank you, Sujit. So in this question, beta, what is given? A laminar flow is taking place in a pipe of diameter 200. Maximum velocity is given, beta. Maximum velocity is given. So just a click. Just a click. So if I take r square as common, so from this equation, this is your maximum velocity or not? Please tell me. Please tell me, isn't it your maximum velocity? Are they say yes or no? Isn't it your maximum velocity? Please tell me. Please tell me. Please tell me. Okay, Vijay, you have given me the answer of this mean velocity. I am interested in this radius bit actually. Mean velocity is 0.75. So this is, now please understand this. Please understand it. This is your maximum velocity. This is your maximum velocity. So this u is 0.75 beta. This u is 0.75 because this is 1.5. So we just have seen that u max by u mean is equal to 2. So this is 0.75. So this is u max. This complete is u max beta. This complete is u max. So this complete is u max. So it is 1.5. The radius is given. The radius is given 100. Please take care of the units. So it will be 0.1. Now from here, if you find your r, from here, if you find your r, it will be 0.0707 meter. 0.707 meters. So it will be 70.7 mm. So at 70.7 mm, you will observe at 70.7 mm, you will observe your mean velocity. Now, similar to these, four formulas are there between two parallel plates. If laminar flow, also known as viscous flow, so if laminar flow is taking place between two parallel plates, these are the four formulas. Similar looking formulas. Similar looking formulas. Yes or no? Yes or no? Similar looking formula. So I will share this sheet. You may refer there. Yes or no, beta? Yes or no? And the last is this Corte flow. So in recent years, this Corte flow is getting very much mentioned. So this is the Corte flow. So if one plate is fixed, other plate is moving, and the flow between the plates is steady in compressible and laminar, then it will be called as Corte flow. It will be called as Corte flow. Now I have covered up to this, beta. I have tried to cover up to this. Turbulent flow formulas I have not mentioned in the sheet also. Okay, so you can cover them by your own. Yes or no? Yes or no? Yes or no, beta? All right. So I hope, beta, any doubt of yours, you may please ask me. After then, we'll be concluding this session. So I hope, beta, this session you find useful. And if you have spent your 6 hours in this fluid mechanics score boosting session, we are now concluding this series of fluid mechanics score booster. So I hope if you have spent your 6 hours, you may feel that your 6 hours had some use. They are not wasted. Yes or no? Yes or no, beta? Yes or no? So in this sessions, beta, I tried, beta, to cover as much as possible. We have solved some questions also. We have gone through all the syllabus of this fluid mechanics except turbulent flow and fluid machinery. Okay. Okay. Okay, beta. Okay. So I hope you guys have liked the video. Okay, and please do like, comment, share, subscribe. Please refer your friends to the GATE Academy. On the screen, you can see the number. On the screen, you can see the website. Okay, please recommend your juniors. Please recommend your friends to subscribe the channel, to join the GATE Academy. Getting my point, beta? Okay. Okay. So thank you very much on behalf of the GATE Academy. This is the end of our fluid mechanics score booster series, and I hope that you like the series. I hope that this will really boost your score to some extent. Yes or no? Okay. So on behalf of the GATE Academy, thank you very much. Thank you for watching the video. Thank you for supporting us. Very best of luck to all of you for GATE examination. Very best of luck for any competitive examination, any competitive technical examination that you are going to do or go for in your future. All right. So thank you very much, beta. So let's end this session. So thanks a lot, beta. Thank you very much. Very best of luck. Please do prepare well. Okay. So thank you. Please do like, subscribe the GATE Academy channel, beta. Thank you very much.